Okay, so we are recording. Responses will be recorded. So again, we learned in Calculus 1, you learned in Calculus 1 some basic antiderivative rules. You can find antiderivatives of some trig functions and polynomials you can find antiderivatives of. And what I'm doing is I'm looking in section 5.3 in the textbook, and there's a table of indefinite integrals in section 5.3. And indeed, a lot of standard antiderivatives. But here's a situation where we want to evaluate the antiderivative of 3x times the square root of 1 plus x squared. Okay. Let me give you a moment to copy this down in your notes. So I believe writing is thinking. So I think it's helpful to, how many find it helpful to write down the examples and have good notes and all that? All right, good, Daniel. Daniel knows what I'm talking about. Susanna, Helen. All right, so we'll pace ourselves accordingly. Excellent. All right, let me give you a moment to copy the example down. Excellent, excellent. Okay, so when we look at this problem, it's clear that, I want to say this, the antiderivative of 3x times the square root of 1 plus x squared, offhand is not an easy antiderivative. So what we want to do is we want to convert this integral with respect to x into an integral with respect to a different variable. We want to make what's called a substitution. The question is, what kind of substitution do we make? Well, when we look at this particular integrand here, what makes the integrand, what makes this integrand here complicated? What's making the integrand complicated?
The square root.
Okay, that's right. Clay and Jonathan agree. The square root function makes it difficult. So what if we were to do a substitution? What if we were to let u equal 1 plus x squared? Okay, u equals 1 plus x squared. How would that affect things? Okay, well, let me go to the next page, and we'll look at the solution. Okay, and I'll mark things as I go. So what I did, or what we did, was we let u equal. Hold on, I don't want any email disturbing us here. Hold on, let me turn my email off for the moment. Okay, so I'm going to let u equal 1 plus x squared. Okay, so that means then that in this integral above, the 1 plus x squared is now u. But what we have to do is we have to transform the 3x and the dx in terms of the variable u as well. We're doing a substitution. We're changing the integral from an integral with respect to the variable x to an integral with respect to the variable u. Okay, so we're doing a this change of variable or substitution. Well, all right. If u is equal to 1 plus x squared, the du dx would be 2x. The derivative of 1 plus x squared is 2x. Now, what I can do here is on this part here, okay, on this part here, I can multiply both sides of that differential equation by dx. And when I do that, on the left-hand side, the dx simplifies. And so I'm left with du equals 2x dx. So, you know, a derivative is a rate. A derivative is a rise over a run. So it's okay to think of a derivative as a fraction. And then we multiply through by dx, that differential. How many remember differentials in Calculus 1? How many recall that? It's traditionally covered, but all right, Helen recalls it. All right, very good. Well, so du is 2x dx. But remember what I want here. I want 3x times dx. So if du is 2x dx, I'll multiply that equation by 3 halves. And this means 3x dx is 3 halves du. See that? And so now everything in this integral is accounted for. Everything's accounted for. The 1 plus x squared becomes the u. So I have the square root of u. And then 3x dx becomes 3 halves du. And so I converted this integral with respect to x to a much easier integral with respect to u. I mean, isn't that fascinating? It's kind of fascinating, right? Well, okay, so I'm going to move. Are there any questions up to here? Up to that step there? Jasmine?
Could you please explain why you multiplied both sides by 3 halves again?
Oh, okay, sure. The reason I did that was because the 1 plus x squared is accounted for in this integral here, but I need to account for the 3x dx. Okay, I need to write that in terms of u, the variable u. So if du is 2x dx, well, if I multiply by 3 halves, I'll end up getting a 3x dx on the right-hand side. So 3x dx is 3 halves du. And now everything in this integral up here is accounted for. So like, for instance, if I had a 5x dx, if instead you have a 3 here, instead if I had a 5, what would I be multiplying? What would I be multiplying both sides by?
5 halves?
That's right. Exactly right.
Okay, thank you.
Okay, you're welcome. You're welcome.
Professor? I have a question.
Oh, yeah, yes.
My name is Lillian.
Clea?
Lillian.
Oh, Lillian. Okay, Lillian. Yes.
I just had a question. So I get why du equals 2x dx, but I'm not understanding why do you want to get the 3x dx on the other side to even make it 3 halves?
You're not understanding why I want 3x dx to, why I want
the other side of the equation.
Because up here, let's see here. Hold on here. Up here, I need to account for this 3x dx. Yeah. I need to replace it with a function of the variable u. Well, 3x dx happens to equal 3 halves du, but that's why I replace the 3x dx with the 3 halves du.
Okay, okay. Thank you.
Okay? All right, very good, very good. Good questions. So, okay, we'll bring the 3 halves. Sorry, Mandy?
I have a question.
So I was wondering where,
Oh,
so under I don't understand how you got 3 halves u 1 half du to 3 halves 2/3 u to the power of 3 halves plus c.
oh, right here, this step here.
Yes, those two under the I.
Yeah, the antiderivative of u to the half. Okay, okay, let me show you that. Hold on, I can clarify that. So if you take a half plus 1 and divide it by a half plus 1, that's going to equal u to the 3 halves over 3 halves, and that'll just equal 2/3 u to the 3 halves. So remember like when you differentiate like uh, a term of a polynomial, you know, the power rule. Remember, you subtract 1 off the exponent for the power rule. Like if you had, like, just as an aside here, if you had, you know, d dt of t cubed, that's 3 times t to the 3 minus 1 power, right? That gets you 3t squared. Well, the antiderivative is going the reverse of the power rule. Instead of subtracting 1, we have to add 1, you see, to get the antiderivative. And that's how we arrive at 2/3 times u to the 3 halves. That's how we get there. If you differentiate, and I know that some of you might need to, you know, practice these concepts. It's been, how many of you have been a little while since maybe you've had calculus 1? Okay, and I understand that. I understand that. So the calculus 2 will reinforce. Oh wow, somebody said 8 years. So it's okay, but you know, naturally, if you're a little rusty on your calculus 1, you just have to review, you know, and you'll be fine. You'll be fine. But that's fine, Javier. Sure.
Professor,
Professor? Yes.
the class is being recorded, right?
It is. It is.
Okay, thank you.
It is being recorded. It is being recorded.
Professor?
Yeah.
The only thing that I'm not getting is, like, how do we get the 3 halves? Like, I don't understand that part. How do we get the 3 halves?
Well, the u to the half, you add, so you gotta increase the power by 1.
Mm-hmm.
And then 1 half plus 1 is, we put that in the denominator. We put that in the denominator. So this is just a rule that you'll have, that you know need to review a little bit, but the antiderivative, if you differentiate 2/3 times u to the 3 halves, okay, and this is all being recorded. Thank you, Mark. If you differentiate with respect to u of 2/3 times u to the 3 halves power, 2/3 comes out front, right? And then you have d du of u to the 3 halves power, and that equals 2/3 times 3 halves times u to the 3 halves minus 1. And that's just going to get you 1 times u to the half power. So indeed, the derivative of 2/3 times u to the 3/2 does give you u to the half power. So it's like you're, when you do the power rule with the derivative, you're subtracting 1. But when you want to get the antiderivative of a variable raised to a power, you have to add 1. And that's how it works. And so just keep that, think about that a little bit, Clea. And after class, of course, I can stay. I mean, generally, I have office hours anyway after class. I can stay a little bit after here to help answer questions. But Clea, does that help you feel a little bit better? Kind of the back and forth here between the power rule and the antiderivative?
Yeah, but I think I just need to rememorize it because I have had calculus one in so long. So.
Okay. All right. Well, and you notice, I'll mention too, somebody noticed this, the integral here, the integral, I call that integral I set that integral, I just call it I, and that's so I can just, I'm working with my integral, that's called I, and here, I end up then getting my antiderivative. I was able to get the antiderivative. That's u to the 3/2 plus a constant. But remember, the original integral was with respect to x. So my answer has to be back in terms with respect to x. And so since u was equal to 1 plus x squared, I got to put that back in. And that's the antiderivative. That's the antiderivative. And let me show you something here. Let me show you something. You might say, well, Dr. Judy, how, is that really the antiderivative? Yes, because if we differentiate one, I mean, you can do a check on it, right? If you differentiate 1 plus x squared to the 3/2 power plus a constant, well, that's just then the derivative of 1 plus x squared to the 3/2 power plus the derivative of that constant. But what's the derivative of a constant equal to?
0.
0. That's right. How am I going to find the derivative of this 1 plus x squared to the 3/2 power? What rule do you have to use that you learned in calculus 1? You have 2 functions here. You have a 3/2 power function and you have an inner function. That's your outer function. And then an inner function of 1 plus x squared.
Chain rule.
That's right. That's right. That's right, Javier. That's right, Clea. The chain rule. The chain rule. So the derivative of the outer function would be 3/2 times 1 plus x squared to the 1/2 power, because 3/2 minus 1 is a half. And then the derivative of 1 plus x squared is just 2x. And so this is a way you can check if your answer is right. Those 2's cancel, and you're left with 3x times the square root of 1 plus x squared. That was our original integrand. And so it worked. Okay. So this is, there's a lot of rules being used here, and you're gonna get better and better at this. If you work at it, right? Okay. Are there any questions before we move on to the next example? I'd like to get, sure. I'll go back here. Hold on. One moment. Okay. Okay, excellent. All right, you're welcome, Jonathan. And again, I guess in the notes here, I did that. I mean, I have the check written down here more formally. We just did it in the blackboard, but there it is. So, all right, let's go to another example. Yes, Mohammed.
Sorry, that was an accident.
Oh, no problem. Okay, okay. Okay. I want to get another example in here. Hold on. Why is there no dx, Shalom? What, you mean like here? You found your antiderivative, so dx is gone.
I'm saying for the answer written at the bottom, how we check the math.
Well, all I'm doing is I'm saying that for the check, good question. The derivative of my antiderivative leaves me with my integrand. If I have the right antiderivative, the derivative of my antiderivative, should give me the integrand, because they're inverse processes in a sense.
Yeah, I hear you there. I'm just asking why there's no dx at the
Well,
bottom.
you're not doing an integral. We did the integral, and we got our antiderivative. Now all we're doing is we're checking to see if the antiderivative is correct. And since the derivative of the antiderivative equals the integrand that we started with, it's correct.
Okay, I hear you now.
All right, very good, very good. Okay, let's look at another one. Okay, and I'll mention the examples I'm doing. So the textbook has very good examples, but oftentimes I will do examples that are not in the textbook. I'll do different examples, just so you have a wider variety of examples. Helen, you're doing all right? All right.
Yeah, sorry, I accidentally left my hand up.
Okay, okay. What I'll do is probably, I want everybody to participate, and I'm worried that, I want people to raise their hands like yeah, I understand that sort of, and then I can just close the hand, I know sometimes I'll close somebody's hand who has a question, but that can be easily remedied, right? So let's look at this now. This is kind of an interesting antiderivative. What's making this problem complicated? I mean, if you had to focus on, we're going to do a substitution. We're going to let u equal something. What would you recommend that u be equal to? What's going to get this problem unlocked?
The sign?
All right. Well, now some of you are saying let u equal the sine of x to the 16th power, but why don't we let u equal x to the 16th power? if I let u equal the sine of x to the 16th power, if I differentiate that, I mean, I can use the chain rule and all, but let's keep the substitution simple. Okay, let's keep it simple. Let's try u equals x to the 16th power. If I do that, okay, well, all right, u is x to the 16th power. So now I have the sine of u, and what's left? X to the 15th dx. I have to write that part of the integral with respect to u. So, well, okay, du dx, the derivative of x to the 16th power, is 16 times x to the 15th power. But I don't want 16x to the 15th power. I want just a 1x to the 15th power. So, okay, I can multiply through both sides by dx. Okay, here. I can multiply both sides of that equation by dx. The dx's simplify out, and I'm left with du. Du will equal 16x to the 5th dx. And so x to the 15th dx is 1/16 du. And that's what's going to go in, that's what we're going to be substituting down here. Now we have the sine of u, and then we have 1/16 du. Are there any questions? How would I get 1/16? Well, Javier, if I look at my integrand up here, I want to replace the x to the 15th dx. And what I know is that du dx is 16 times x to the 15th power, right? Well, if I want just x to the 15th power, I have to divide both sides by 16. In other words, what I'm doing here is I'm multiplying by 1/16 on both sides. See that? And then that 16th here is going to simplify with this 16. Okay, that was a 1/16 on the right. And you're left with 1/16 du equals x to the 15th dx. So our integral now becomes the integral of the sine of u times the 1/16 du. You're welcome, Javier. Excellent, excellent. Good questions, good questions.
How did you get negative cosine u?
Oh, the antiderivative of the sine is minus cosine. That's one of your antiderivative rules.
Okay. I had a question. So during our exams, are we allowed to use our notes or no?
You will, you got to be a little careful about this. You're going to need to know some of your, no, I don't, I definitely, I don't want students to use notes during the exam. The college has certain policies for calculus, like 1 and 2, and you know, the notes are something that generally, you know, like you have to be able to know these antiderivatives without referring to notes. So, but let me refer you to something here. I'm gonna, well, hold on. Let me just do one thing here. So I'll get back to this. But the antiderivative of sine is minus cosine. Let me show you something. Maybe I can do this little trick here that actually a student taught me. What's the derivative of the sine? Now this is an aside here. I'll tell you what. Yeah, this is just an aside. The derivative of the sine is what? Good, is the cosine. What's the derivative? What's the derivative of the cosine? Minus sine. Good. What's the derivative of minus sine? What would the derivative of negative sine have to be? Almost right. It'd have to be negative cosine of x. Good. And then the derivative of negative cosine of x back to sine of x. So the reason I'm showing this is students tend to find derivatives easier than antiderivatives. So I think, you're probably pretty good with this. But then if you say, okay, well, what's the antiderivative of the sine of u? Well, to get the antiderivative of the sine of u, you just go the other direction. See, in the circle. So the antiderivative of the sine is minus cosine. Okay. How many finds that helpful, that little circular chart here? Okay, wonderful, wonderful. Okay. Excellent, excellent. Thank you, thank you. So, okay, is our answer going to be negative 1/16? Is our antiderivative negative 1/16 cosine u plus a constant? I mean, are we done with the problem? No, what do we have to do? What do we have to do?
Check.
Well, we have to switch back to x. The original integral was an integral with respect to x. So our answer has to be with respect to x. And so indeed, we're going to substitute back in for u. U was x to the 16th. And so the antiderivative is negative 1/16 times the cosine of x to the 16th plus a constant. Okay, one moment. Okay, we'll go back to that page. Let's make sure Javier's good here. Okay, Javier, you're good? Okay, let me go then to the, very good, and then here's the, final result. So you see, this little technique, making a substitution, is really helpful. It allows us to expand our ability to find antiderivatives. And that's one of our key goals in Chapter 5, is to expand our capabilities for finding antiderivatives of functions. Let me show you one thing here. I want to bring up, let me just bring this up. Let me go in here. One moment. Okay. What I'm doing is I'm going to the ebook. Now this, you see there on the top, it says My E, like this is your like student view in WebAssign, My eBooks. Okay, so you click on My eBooks, and we're going to go to Calculus here. Hopefully it'll show. Well, I think I have to go in. Now I got to go back into the ebook, and I want to go to chapter 5. So I want this on the recording, and let me see here. Let me just go here to section 5.3. And here is this table of indefinite integrals. Hold on, everybody. Yeah. There's the table of indefinite integrals. So how many recall this from Calculus 1? Finding this table. Okay, good, good. I mean, we're just building on what you learned. Yeah, and actually in Calculus 1, I teach Calculus 1. I know these formulas are derived, most all of them. And yeah, are there any questions on this?
I have a question.
Oh, yes, Helen.
So for, I guess, either of the questions, I just realized, so I guess for example 2, you know, there's like the x to the power of 15 in front of like the sign x to the power of 16 dx.
Yes, it's the.
Sorry, so are we just supposed to like ignore the x to the power of 15 and then like move on with the problem?
We did. It turns out in hold on here. In that problem, you know, it turns out that we needed the x to the 15th, right? Because again, you're letting u equal the x to the 16th power. So this here, this becomes the sign of u. We're transforming our integral to an integral with respect to the variable u. So the sign of x to the 16th power becomes the sign of u. But we have to worry about x to the 15th dx. We have to replace that. And we are able to. See? Now, if you, yeah, you see that? And then you know, this here, x to the 15th dx becomes 1/16 du. And so you end up with this resulting integral below.
Okay, thank you.
All right, excellent. Very good questions. So I'm going to give you about 15 minutes here to work a little bit on the classwork, and we're gonna do some more substitution examples. But let me go ahead and stop the recording here.